Okay, well, we're going to wait a few more moments for the everyone to enter the virtual room here. We are going to have the parallel session 6, Lunar Geology and Landers. I'm Noah Petro, and joined by Sarah Valencia. We'll do a more formal introduction in a moment. As a reminder, we're aiming for 10-minute talks. Give a warning at 8 minutes, another warning at 10, and then we will de-Zoomify you at 12 minutes to move on to our next presentation. We do have time for discussion and a break at the conclusion of the session, and so we will try to keep on time so we can respect that. And I do see that our first speaker has entered the room, so Sarah, if you're ready, we can get started.
Yeah, okay. Hi, everyone. Welcome to the Lunar Geology and Landers section. Our first talk is by Lingji Sun on the multispectral imaging and hyperspectral profile of the first dissection for core 73002. So take it away.
Okay, can you hear me? Okay, thanks. So today I will introduce some preliminary results from the spectral measurements of the first dissection for the Apollo 17 core 73002. So this core was collected at the Station 3 during the Apollo 17 mission, and this station is located on the light mantle down the South Massif next to the Lara crater. Here I have a panorama of the Lara crater. So the core is collected in here, and there are also some trench soils collected next to it, which can be used as reference soils for this core. So the double drive tube is now curated at the Johnson Space Center. The whole core is about 60 centimeters in length. So the lower segment is the 73001, and it's sampled about 70 centimeters in depth, but it haven't been opened yet till today. So here is the look of the 73002. It's the upper segment, and it is sampled about 30 centimeters in depth. So when it's extruded from the tube, it's compressed to about 18 centimeters. This core was opened in last December. Our role is mostly measure the spectral data for this core. So the whole core is curated within this glove box. If you look at the schematic diagram on the right, we have to observe from the through the glass wall of this glove box, which limited our measurements to only at visible and near infrared wavelengths. So we have two sets of measuring systems. One is the multiband imaging system, and the other is the hyperspectral system. So for the multiband imaging system, we covered the wavelengths that is similar to the Clementine ultraviolet visible camera, and the hyperspectral system is covering 500 to 1700 nanometers. So this figure is on the left is the photograph of the whole core, and the red circles are the hyperspectral footprints along the core. The two figures on the right are the multiband imaging results. So the middle one is a reflectance image mosaicing of the whole core at 570 nanometers. We can see the systematic darkening effect on this image, and we also made a false colored image of the whole core. The red channel is the 750 versus 415 nanometers, which is sensitive to the spectral reddening effect. And we can see that on this figure on the right, there's this very obvious darkening effect from bottom to top of the core. And these are this spectral darkening and reddening are due to space weathering. So when we plot the whole core over this ratio plot, so the y-axis is the 950 versus 750 nanometers. The x-axis is the 750 nanometers. We can see that there's not a lot of variation along this iron axis, but along this optical maturity axis, there's a wide span. So we use these equations to calculate the iron abundances and OMAD values, and also the titanium abundances. Then we derived these maps. So the top one is the optical maturity. So on the left side is the top. From bottom to top, we can see this increasing in maturity. But for the iron and titanium, we don't see a lot of variation. It's pretty homogeneous along the whole core, suggesting this core might be sampling the same regolith stratigraphy. So when we plot the OMAD variation along the whole core, we can see that the most fresh soils occurs around 2/3 from the top. And that's about 20 centimeters of the original sampling depths. And when we apply this sampling regolith reworking depths to the equations derived by Dr. Morris et al., we can derive this regolith reworking time at 135 million years. And this is consistent with the cosmic re-exposure time of rocks collected at the same station to the core. And for the hyperspectral measurements, we can see something similar to what we observed from the multispectral data. That is the systematic darkening, and when normalizing the data to 750 nanometers, we can see this reddening effect. But there's no obvious weakening of spectral bands. Might be the reason of these narrow iron abundances along the core, or it's influenced by the grain size variations along the whole core. So we developed a radiative transfer model that can unmix both minerals and chemistry at the same time. So when we apply this model to the hyperspectral data we measured, we can see a lot of plagioclase and low calcium pyroxene. And so the blue circles are from the modeled mineral abundances, and the red dots are from the XRD measurements of the model abundances for the reference soils collected next to the core sample. We can see a good consistency from this two data sets. And the magnesium number we derived is 61, which is consistent to those soils collected at the same station. To conclude, we observe systematic darkening and reddening from both multispectral images and hyperspectral profile. We mapped the iron and titanium contents for the core, and no obvious computational stratigraphy is observed. So from the OMAD variation, we derived a regolith reworking depth at 20 centimeters, corresponding to 135 million years of reworking time. The model abundances derived from radiative transfer modeling and hyperspectral profile show abundant plagioclase and also pyroxene exists within the core. And with that, it's the end of my presentation. Thank you for listening.
Okay, thank you for that, Lingji. The floor is open if anyone has any questions for our speaker. Okay, we have a question. The core was taken from a landslide deposit, yes. Do you attribute the homogeneity to a landslide or just to a regular regolith processes?
Oh, I think this homogeneity is one because it's on a landslide, and also it's kind of on the ejecta of this lava crater, so kind of both.
All right, thank you, Lingji. Before we continue on, I did want to take a moment to congratulate you on the successful defense of your PhD thesis yesterday.
Thank you.
I can't speak for everyone, but I can absolutely assure you that I would not have been able to give a presentation the day following my PhD defense. So I am both very proud, and I want to take a moment to congratulate you publicly for an awesome job both yesterday, of course, and today. And I assure you that eventually we'll be able to hold meetings and we'll be able to congratulate you in person. But for now, a virtual Zoom salute for you. Congratulations.
Thanks.
And excellent backdrop. So Sarah, if it's okay with you and with Lily, we'll move on to our next presenter. And by the way, excellent job staying on time with that presentation. So our next presenter is Yun Huang, diverse rock types detected at the Lunar South Pole Aitken Basin by the Chang'e 4 mission. Again, I'll do an alert at 8 minutes, 10 minutes, and then 12 minutes we'll move on. Take away.
Hi. I should say good morning. Actually, it's night here. So today I'm going to present some results of Chang'e 4 mission. We detected different rock types near the landing region. If you need more detail, please read our paper published in Geology. So the name of the mission is Chang'e, not change, not Chang'e. Even back in Apollo times, there was jokes about the beautiful lady. So for the Chinese lunar exploration programs, there are 3 phases. First is orbiting, which consists of Chang'e 1 and 2, and then landing, which includes Chang'e 3 and 4, and this year Chang'e 5 and will be launched and collect a sample from the near side of the moon. But today we will focus on Chang'e 4. As you all know, if you want to land something at the backside of the moon, you need a relay satellite. So the relay satellite Trailblazer was launched 2 years ago, and then 1 year ago, the lander and the rover was launched, and it successfully touched down on January 3rd, 2019. There are several instruments on the lander and the rover, and today we are going to talk about some data acquired by the descending camera, parametric camera, topographic and geology camera, and the visible and near-infrared spectrometer. As you know, there are several interesting questions remain for the far side of the moon, especially for the giant hole at the far side. First is there any null crust or upper mantle materials exposed? The second is, can we observe differentiated impact melt sheet? And the third is, what's the composition look like for the far side melt basalt? As the landing side within a crater named Von Karman, at the north west of the SPA crater. As you can see from the orbital data, the very superficial material for the landing site is probably from the impact crater Friesen, just northeast of the Von Karman crater. And what can we tell from the in situ observations? Can we see mantle materials? So we will talk about the first 4 days results for the rover, which has been traveled almost 500 meters now. But today we only focus on the first 200 meters. As you are all familiar with the spectral, you can see here we show the spectral of the regoliths observed in the first 4 days. And in this small picture here, this is the footprint of the sphere detector, and you can see the red slope of the regoliths and the features around the 1 micron and the 2 micron. We collaborated with Paul Lucy and used the mineral lookup table. We removed the continuum between 750 to 1550 nanometer, and we fixed the grain size to 17 micron, and we set the MG number to 65, and we used 4 methods to evaluate the spectral fit. So we plot the mineral abundance to the program to the plots above, and as you can see, there's some variations, but most of them are dominant of plagioclase and pyroxene. And as you can see, our results about the mineral abundance observed in situ is consistent with the previous work by our colleague using Kaguya and my data using similar mineral lookup table approach. So let's switch gears to the cameras. As you all can see in this picture, we see 2 groups of rocks with different tons of tons, and one group is dark tons, like this one in the middle, and we zoom it in with the image, and you can see there are some white spots on the dark rock. It could be plagioclase, finalist, or they can be pits created by micro impact. Unfortunately, we didn't take visible and near IR spectral of this rock because the rover was busy doing check and taking images to the lander at that moment. So at the end of the second day, we encountered a bunch of rocks. One of them, in front of this bunch of rocks, we took a visible and near IR spectral of it, and this is the first in situ visible near IR spectral of a lunar rock. We named the rock informally as Qiyuan, which means unexpected encounter. So when we zoom in to the rock, and we can see similar white spot on the rock, which has similar explanation as I previously explained. And this is the image taken from the visible near IR spectrometer, and you can see the footprint of the sphere detector. Okay, here I show the spectrum of the rock above the spectrum of the regolith. As you can see, it's a rock, so it has relatively deeper spectral features around 1 and 2. So we try to analyze the spectral quantitatively. So we remove the continuum, and we compiled the spectral to the spectral available for the Apollo samples. And as you can compare the center locations and other spectral features I will mention later, we found that the spectral is similar to materials with dominant pyroxene and plagioclase.
Net, you're at 8 minutes, by the way.
Oh, thank you. So we compared the spectral to the remote sensing MQ data as well, and we found similar results. And as you can see from the figure on the right corner, previous colleagues' results are similar to the results we found, and the materials from the ejector of Thyssen crater is similar to the landing side and to the in situ measurements. So we did some spectral analysis. As I mentioned before, we calculate the 1 microband asymmetry with the 1 microband center and 2 microband center, and band area ratios, which means band area of 1 and 2. And so we plot all of this, and we see the difference, the distance between the rock and all the selected Apollo samples, and we found out the rock Qiyuan is likely composed of pyroxene and feldspar dominant assemblage with at most minor olivine. So how should we interpret the implication of the rock? As we can see from previous work like Otaka 2014, at the center of SPA basin, it's most likely there's a central depression, which may indicate most of the impact melt. And at the location of Von Karman crater, it most likely the ejector is ejected from the Thyssen crater, which is quite far away from the outline of
And
the impact.
You're at 10 minutes, by the way.
Yeah, so we think mostly the rock Qiyuan is like a representative of lunar crust, not from the mantle. So the take-home message is Qiyuan is likely from Thyssen crater, which is consistent with orbital observation, and Qiyuan and nearby regoliths indicate a mineral assemblage of feldspar and pyroxene. We don't see olivine-rich materials reported by our colleague. I will stop here, and I'm happy to take questions. Thank you.
Great, thank you. We did have one question in the chat. I'd suggest actually you go ahead and answer because you directly in the chat after your talk. So we have about 40 seconds. If there's anyone who wants to raise their virtual hand and ask a question out loud.
Yeah, it's just Clive. Were you able to deduce a whole rock magnesium number? Because Otaki also suggested the crustal materials are higher in magnesium number on the far side than the near side.
It's a good question. I don't think we can derive accurate number of mg now, but I think people are trying to derive the mg number. I don't know whether I answer your question.
That's fair enough. So future more work to do.
Yeah, exactly. Thank you, Clive.
Okay, why don't we go ahead and move on to our next speaker. Our next speaker is Li Chao, who will be speaking on mare domes and mare tranquillitatis identification, characteristics, and implications for the oldest lunar volcanism.
Hello, everyone. Can you hear me and watch my slide?
Yes.
And we can see your slides.
Okay, so I will go. So hello, everyone. Good day and good night. Good to be here to talk about our work on the mare domes in mare tranquillitatis, identification, characteristics, and the implications for the oldest lunar volcanism. I'm Lunar Trailblazer from Shandong University at Weihai in China. Mare domes are small and general circular structure with convex upward profiles. They usually have very gentle topographic slopes, and they are among the most common undermember volcanic landforms on the moon. So studying their spatial distribution and nature will provide very important information for controlling their eruptive process, magma composition, and also nature of the magma source region, and that improve our understanding of the moon. Previous works have already identified over 300 mare domes on the moon, mainly use telescope and orbital photographies. So why we still looking at them? Because many domes are very generally slow. Many are generally less than 5 degrees, and many even less than 1 degree. So they are not easily identified. Many of the lunar domes can be only detected from images very low sun emulations. But obtaining such image is very difficult, and the kind of coverage is very limited. But now we have very good real data. We have the global coverage, high resolution, and the high precision topographic data, which provide a very powerful tool for identification, identify and study the mare domes feature on the moon, like the SLDM topography data calculated from Kaguya TC-DTM and LOLA topography data, which has a resolution about 60 meter and a vertical accuracy of about 3 meter. Shown here is the example. The upper one is the dome identified previously. We can see a very circular feature with a very beautiful subameter pit crater, and the showing below is a new dome identified by us. Here is the low sun Kaguya TC image. We can see a rise feature, but we cannot make sure whether it's a dome feature or not. But the topographic data and the map and the profile shows clearly the mare dome. So we started a project to search mare domes on the moon, and also study their detailed nature. And as the first step of this project, we focused on mare tranquillitatis. For short, I will just call it mare T, which have many mare domes, and also identified as a large shaded volcano by spurities. We use the SLDM topography data with other topography and images to evaluate the previous and mary dome identifications and also search new domes. And then we study the detailed lecture of each dome. So here is Mary T is the landing target of the Apollo 11 mission. So it's one of the best studied Mary and Moon. It has the highest titanium content basalt on the Moon, but it also shows sectional composition variations. So this indicates a very complicated and multi-stage volcanic eruptions. And use crater counting method, Hessinger et al. Calculate the age of this Mary basalt. We found that all but only one Mary basalt unit are older than 3.5 billion years old. Put this age in the context of global Mary, we can see that Mary T is absolutely the oldest Mary on the Moon. This picture showing the different age, ages of different Mary units within the many Mary. And Mary T is here. Oh, sorry. So firstly, we use the low topographic data to evaluate the previous Mary identification. There are generally 3 major studies. We confirm some ones, but also reject some Mary dome identifications. So in total, we confirm the 93 domes, and we also find the 7 possible ones, and 10 are negative identifications. Then we use the topographic data to search new domes in Mary T. As a result, we identify 96 new domes and also find many possible domes. So in total, combine ours and the previous identifications, we have 189 confirmed domes, also plus nearly 100 possible ones. So Mary T contains one of the highest density of Mary domes among the entire lunar Mary. This is the area density of the Mary domes in the Mary T. We can say 2 obviously concentrated areas. One is in the north edge and another in the south region. Here are some examples of the Mary domes in Mary T. We can say some are generally very circular or generally circular, and some are elliptical, or some are generally irregular. Many domes have subrepeater features. Here are the topographic profiles. Then we measure their dome-based diameter. We find that they are between 2 and 23 kilometers. This is generally within the range of previous studies. However, our new data, the high resolution topography, enable us to discover many smaller domes. We also measure their height and find they are between 20 and 400 meters. And then we study the subrepeater crater features of Mary domes. They are commonly, though not always, observed at the tops of Mary domes. Among our domes, we find 124 have subrepeater features, and over 8 have possible ones, and others lack of it. And the presence or absence of subrepeater crater seems to be independent from the diameter, height, or shape of the host Mary dome feature. Here's the distribution of the distribution map of the subrepeater crater identifications. We have different color means different possible ones and confirmed ones, or just absence. Here are some examples of the subrepeater craters. Some are generally circular, and some are elliptical, and some are more irregular. A very unusual shape of the subrepeater crater are the very elongated piece. They are very long and narrow. We don't see such shape for Mary domes, but we see it for the subrepeater craters. We measure their diameter, find they are less than 4 kilometers, and we also plot the subrepeater diameter against the dome-based diameter. two previous studies have found a linear relationship between the two diameters, but our catalog finds that it shows a very wide range, and we don't have such simple relationship. This is probably because our catalog have very huge meridome problem. We have nearly 300 meridome, but this two function is fitted from over just tens of meridomes, and we also calculate their depths and
You're
we
at 8
find
minutes.
okay, and we find that their ratio is their depth over diameter ratio have a wide range, and nearly half are shallower than impact craters on the moon. Another interesting finding is that we found that nearly half submeter Peter craters, their floor is topography lower than the surrounding Mary. This cannot be determined from image data only, and suggests a significant submeter Peter collapse process during the formation of the submeter Peter crater. And then we also studied the composition. We find that they have a wide range of titanium content, but their iron content are really homogeneous. And finally, we also check the age of the background Mary. We find 276 domes are located or just near 19 crater population dated Mary unit, but only one domes are hosted in Mary unit that are over 3.5 billion years old. So put this in the context of the global Mary ages, we can say these are generally contemporaries with the peak period of global lunar Mary, but only span a very narrow time period, just 1/10 of the longevity of lunar volcano. This indicates that the small shade building eruption may be a prevalent eruption style in the earlier stage of lunar volcano. Okay, finally, here are our conclusions. We find nearly 200 meridomes and another 100 possible ones, and many of them have submeter craters, and we don't have find a simple relationship between the submeter Peter diameter and the dome base diameter. And Mary T is the oldest Mary on the moon, and so this means that small shade building eruption may be a prevalent eruption cell in the initial stage of lunar volcano. Thank you. I will leave my conclusion here and take questions.
Great. Do we have any questions from the room? I'll ask, did you have any indication that there may be any smaller scale compositional variations of these domes? You showed the titanium map earlier on and the regional scale, but do we see any small scale variations immediately surrounding these features?
You mean the composing of the Mary and the surrounding Mary? Is that your question?
Mm-hmm. I think so.
Actually, we have already do that. We find that so we have nearly 300 meridomes, and we find nearly 30 domes. They have very different titanium content with the surrounding Mary. Yeah, we found some.
There's a question in the chat but we unfortunately have to move on to our next presentation. So I'd ask that you would follow up with Jeff Gillis Davis's question in the chat window, and we'll move on. Thank you for your presentation.
Okay.
Our next speaker is Melissa Battler, who will be talking on autonomous soil assessment system, contextualizing rocks, anomalies, and terrains in exploratory robotic science. And of course, there's an acronym, AS craters.
Great, thank you very much. Let me just get my slides here.
We can see your
Hopefully that's
PowerPoint
working. Are you able to see the correct
display.
view now?
We see the whole majesty of PowerPoint.
All right. Yes, and not my speaker notes. Good. Then I will get started. Thank you very much. Good morning or afternoon, everyone, depending on where you are.
We now see your speaker notes.
How did it switch? That's crazy. Oh man.
We can read what you want to say. That's perhaps less interesting.
That's the weirdest thing. Okay, I have very bad luck with this. Let me see.
So make sure you go into presenter mode.
It is. It's just, it like really switched screens after it was already sharing. All right, it says it's the right one. You now see the full majesty of PowerPoint again. No, you don't. Now you do. All right, I'm hoping this is working. So good morning or afternoon again. So my name is Melissa Battler, and I'm a planetary geologist and the Chief Science Officer at the Canadian Space Exploration and Robotics Company, Mission Control Space Services. And at Mission Control, we develop computing solutions that support planetary science missions by enabling onboard and offboard autonomy, and thereby streamlining mission operations. We test and validate our software through analog missions as well. So I'll mention that my co-author, Kaisa Braimalwala, who's an engineer, is listening in and can also help answer if there are any more engineer-related questions at the end too. So today I'm going to talk about the science autonomy tool that we're developing for lunar exploration. And as mentioned, it's called ASAS Craters. Although I will talk largely in the context of robotic exploration, I will touch on Artemis as well in the last couple of slides. So as several speakers discussed yesterday, science operations in the new paradigm of commercial lunar missions, as well as Artemis, will differ in significant ways from any previous planetary missions that we've experienced. Mission operations teams and science backrooms will face new challenges, and early robotic missions will be short in duration with limited onboard autonomy. There will likely be a lot of data generated on board, which will need to be triaged, and there will be a highly constrained downlink capacity. Tactical cycles will need to be rapid and may even include real-time live streaming of data rather than the punctuated downlinks that we're a little bit more used to in planetary operations. In any case, decisions will need to be made very quickly due to these short durations and short turnaround time. Analyzing terrain in backrooms can be time consuming and relies on downlinked imagery that may be, in these cases, compressed or downsampled due to bandwidth or downlink restrictions. Additionally, it can be difficult and sometimes serendipitous to quickly catch novel features or features that may have been seen before or are rare to find. So in this new commercial paradigm, delivery and operations companies face pressure to maximize scientific return and to lower costs. These are challenges that we embrace because ultimately we face the risk of needlessly leaving data behind on the moon, and no one wants that. So this is what's driving the demand for more onboard autonomy. To address these challenges, we're developing an onboard science system, which is called ASAS Craters, and it's designed to support and aid lunar scientists during mission operations through autonomously classifying terrain. So in its current design, a couple of algorithms will run on board. So as a rover or even an astronaut moves around and captures standard RGB imagery, our algorithms will perform terrain classification and novelty detection. This happens at a rate of about 1 hertz. So these algorithms are based on deep learning models, which are informed by our science team. So we've previously developed and field tested our terrain classifier to TRL5 for the Mars analog study SANDY, which was deployed in Iceland last summer, and this is part of the NASA P-STAR program. To provide a little bit more of the scientific context, so a few examples of the types of lunar specific terrains or terrain features that we're able to autonomously classify are rock fields, regolith tone, hills, craters, so different features of craters, including crater size, crater freshness, crater fields, and more. So the scientific rationale for, say, crater freshness is that crater freshness relates to the age of the crater. So by examining craters with different degrees of freshness, the way in which the lunar surface ages can be better understood. One more example, so crater fields provide insights into the timing and mechanisms of the moon's bombardment history. So craters of similar size and alignment relative to larger crater, as we know, could be consistent with secondary craters. So such crater chains could provide access to materials from different regions of the moon. So being able to quickly and autonomously identify, like, hey, look here, this is a feature of interest, might help to address some science goals related to that. Additionally, a variation in the tone of highland or mare terrains and regolith can be useful to help pinpoint areas of interest for determining variations in composition and age. So yeah, by quickly doing this, we can hopefully buy science teams a little bit more precious time to be able to take a more in-depth look at the features that are of interest, or to perhaps request higher resolution images where only compressed images have been sent before. So on the side of novelty detection, we're considering approaches to deal with known features that are relatively rare, such as, say, pyroclastic deposits or outcrop, or even a meteorite, as well as anomalous looking features based on morphology and coloration. So I've shown on the slide here some examples from previous missions. So beyond this, we're interested in exploring the use of other cameras, how our classification technologies can be used with multispectral cameras or remote or micro imagers to get a deeper classification of mineralogy and composition. Our system can also then project the results to the ground plane to aggregate data onto uniform mapping tiles. And this can hopefully provide context and scale and make it easier to analyze results using GIS tools. Once we finish prototyping this year, our next goal is to build an application to enable autonomous instrument targeting and potentially also downlink prioritization. So overall, these data products are compact terrain representations that can be more efficiently downlinked in tight operation scenarios with limited time allowed at any given stop for science data analysis due to mission constraints. They can potentially aid backroom operations in a number of ways. First, by allowing for faster analysis of imagery. Second, by detecting these novel features that a human operator may miss due to the demands of these rapid tactical cycles. And also by allowing for easy integration into GIS tools to allow for, say, overlays with orbital data or whatever else. And additionally, when used on board the rover, our algorithms can additionally boost science operations by maximizing what can be observed in compressed low quality imagery. So say, for example, the science team is only in a given scenario able to receive these really compressed images, while on board the rover, these algorithms can run in kind of in like a low file size sort of compressed way, still able to convey some of that really important information.
8 minutes.
Thank you. And by allowing for the autonomous targeting of science instruments and cameras, supporting autonomous navigation of targets of interest as well. As a software-focused company, we're partnered with Cyclos Technologies, a leading provider of flight-qualified embedded systems. So together, we can offer the solution integrated onto a commercial off-the-shelf computer that has a low cost and low size, weight, and power profiles, high-performance computing to enable state-of-the-art technology like deep learning. So it's a multi-mission system designed to be an auxiliary payload component that can be easily integrated onto your mission or lander-based payload suites, or potentially even into an astronaut suit. As a computer, it can be reprogrammable in flight to some extent as well. Right now, we're engaged with several delivery companies that are close to securing flight opportunities to demonstrate the system in 2022 and 2023. Ultimately, this has to meet the needs of scientists and their payloads, so we are eager to get inputs from everyone and the wider planetary science community on how this can be integrated onto different missions to offer the benefits of science autonomy as relevant to you. So finally, in Artemis specifically, there are lots of neat things we could do given the number of cameras that will be on different platforms, including on astronaut suits. So ASOS creators could be used to leverage these cameras to do local terrain analysis and data aggregation in real time to support crewed and robotic exploration in cooperation. For one example is that if an astronaut is doing an EVA focused on one particular task, but their camera feed is still taking in imagery, an astronaut that's not focused on those terrain features, the software could alert the astronaut, could automatically kind of detect features of interest and alert the astronaut if like a novelty feature of interest is detected in the images beyond what the astronaut is actually looking at actively. Beyond the moon, we have lots of other applications that we're interested in all over the solar system too. And I'll just wrap up by giving a shout out to our team. This project's been funded by the Canadian Space Agency, and I've listed our science team on the slide as well here. Of course, we're very thankful to everyone for their input and some good work on this project. So I'll leave it there and just thank you very much for your attention.
Okay, great, thank you. We have a couple questions in the chat. First one up is from Jeff Gillis Davis. How does this tool compare to the rover science autonomy using hypothesis mapping? There was a talk yesterday by Elder Noah Dobera on hypothesis maps. So you have a comment, and then you have some follow-up questions as well.
Yeah, yes, we're wondering that as well. We heard that talk and we're not actually sure, but we definitely want to follow up and chat and see where there might be some interesting overlap. I think there could be some good synergy there.
Okay, you have a couple more questions for you in the chat, but I think we need to move on now. Our final speaker in the session is Cari Donaldson Hana, and she'll be speaking about mapping the composition of the moon using thermal infrared spectrometry, current and future observations from orbital and landed missions. Take it away, Cari.
Great. Can you hear me now?
Yes, you're good.
Okay, perfect. Thanks. So much of what we know about the moon from thermal infrared wavelengths really comes from the Diviner Lunar Radiometer, which is one of 7 instruments that's on board NASA's Lunar Reconnaissance Orbiter, which was launched in June of 2009 and has really been providing the lunar science community with a rich data set ever since that launch. And to date, Diviner has collected over 1 trillion radiometric observations of the lunar surface. And so this is a really robust data set. Diviner is a 9-channel radiometer that we see here in this image. It has 9 channels that are distributed between 2 identical bore-sided telescopes. Telescope A, which is on the left, hosts 6 of Diviner's channels, 2 solar channels, 3 narrowband channels near 8 microns, which are used for compositional mapping, and then 1 broadband mid-infrared channel between 13 and 23 microns. Telescope B, which is on the right, hosts 3 of Diviner's broad far infrared channels between 25 and 500 microns. The 4 broad channels between 13 and 200 microns are used for mapping surface temperature and physical properties. And so these are the boulder index maps and rock abundance maps and thermal inertia maps that you also see from the Diviner team. Diviner's 3 8-micron channels were specifically designed to map the Christensen feature. And the Christensen feature is this emissivity maximum that we see on the spectra here in the right, that's denoted by the vertical line and the CF. And we chose to these channels specifically to map the Christensen feature because you can see that it shifts systematically with composition. Plagioclase has very short CF positions. Pyroxene has intermediate CF positions, while olivine has long wavelength CF positions. And so this spectral feature can be used to really effectively map composition across the lunar surface. And it has. And so some of the highlights from those diviner observations, particularly the compositional mapping, includes work by Tim Gloch and others who've identified volcanic constructs with very short wavelength CF positions, which is consistent with highly silicic materials. And here's just a few examples that we see across the lunar surface. These evolved magmatic materials provide really important constraints on the thermal evolution of the lunar interior, as these materials suggest that portions of the lunar interior were warmer for longer periods of time than what we previously had thought. Jessica Arnold did a really nice piece of work where she investigated olivine-rich exposures that had previously been identified as possible mantle deposits and showed that the CF position for most of these exposures are actually at too short of a wavelength to be composed mostly or predominantly of olivine, and instead must include large abundances of plagioclase. So this suggests that these materials most likely originated from the lower crust or the crust mantle boundary rather than the lunar mantle, which had been suggested when only investigating these regions with visible and near-infrared data. And we've also been able to investigate the CF position for regions that previously were identified to be spectrally dominated by plagioclase. And this is certainly near and dear to my heart and something that I focused on. We've been able to use the diviner data in an effort to better understand the compositional variability of the moon's anorthositic crust. And what we found is that much of the moon's crust is composed of a highly calcic plagioclase, which is similar to what's found in the Faroan anorthosites, which really places new and important constraints on any magma ocean model for the anorthositic highlands formation. Now, while we've learned much from the diviner data set, and we're still learning even to this day, there's two new exciting opportunities that I'm going to talk about today. The first is the Lunar Compact Infrared Imaging System, also known as LCIRIS. And LCIRIS is led by PI Paul Hain from the University of Colorado Boulder. And this instrument was selected as one of 12 instruments in the Lunar Surface Instruments and Technology Payloads call. It is a rebuild of Ball Aerospace's Cirrus CubeSat instrument, which launched into low Earth orbit on December 6, 2009. Currently, it's manifested on the CLIPS lander mission to the South Pole with Masten Space Systems. The main science objectives of the LCIRIS mission include determine the moon's surface composition at small scales, determine the small scale thermophysical properties of the moon, as well as indicators of rover and astronaut trafficability, and also determine the moon's volatile cold trapping potential at small scales. And this is better for understanding lunar volatile transport and cold trapping of volatiles. LCIRIS will accomplish these science objectives by taking thermal images of the lunar surface using 4 infrared bands between 7 and 14 microns and using an onboard calibration system. 2 of the narrowband channels, those at 7.8 and 8.28 microns, are similar to the diviner channels, and all 3 of the channels are similar to those on Lunar Trailblazer's Lunar Thermal Mapper, which I'll discuss next. We did optimize the position of these bands for 2 different things. First, For the polar temperatures, we're expecting much colder temperatures at the poles than we would for global temperatures, which is what the diviner bands were optimized for. And we also optimize the bands for the feldspathic materials that we expect at this landing site. Thus, for the first time, we're going to have in situ surface measurements from L-series, which is going to provide really critical links between the very small scale surface measurements that we're going to get from L-series with those from orbit for Diviner and Lunar Trailblazer. So in other words, L-series is going to provide the first ground truth measurements of the surface that will greatly enhance both the Diviner and Trailblazer investigations. The second opportunity for investigating the composition of the lunar surface comes in the form of Lunar Trailblazer. And this is a small sat mission that was selected in the last simplex call and is led by PI Bethany Ellman through Caltech and JPL. And Bethany gave a really excellent talk giving an overview of Lunar Trailblazer on Wednesday. So I would encourage those of you that didn't see that talk to go back and watch it online. Lunar Trailblazer is going to address major scientific questions about water on the moon, particularly its abundance and water cycle. It's also going to forge a path for future exploration by evaluating locations of the operationally useful deposits of water and providing compositional base maps for the landing zones.
8 minutes.
Trailblazer will accomplish these science objectives using two four-sided instruments. The first is HVM cubed, a JPL-built imaging spectrometer that will measure reflectance across the 0.6 to 3.6 micron spectral range. And then Lunar Thermal Mapper, a multispectral thermal camera with 15 infrared channels, which is being built by the University of Oxford. 11 of these spectral channels are across the Christensen feature region and will be used for compositional mapping. 3 of those channels are similar to Diviner's 3 8-micron channels, and those are highlighted in these green boxes here. And then 3 channels are also similar to the L-series bands, which I've highlighted in blue. And so Lunar Thermal Mapper will give us 8 additional bands as well as enhanced spatial resolution, which will allow us to better determine surface compositions for the targeted surface regions and investigate some of those areas of geologic interest that I mentioned before, including the highly silicic volcanic constructs, areas that are rich in olivine, and also areas rich in plagioclase. And so just to summarize, Diviner thermal IR observations of the moon are a powerful tool for constraining compositional properties of its surface. It's a really large and diverse data set, and I would encourage those of you to go take a look at the PDFs and the website just to download and use some of that data. Comparisons between Diviner orbital observations with L-series high spatial resolution surface observations will provide critical links between the surface and remote observations. And this really will enhance the interpretations of these global remote sensing observations. Targeted Lunar Trailblazer observations, which we're going to get additional spectral content with, will further our understanding on the formation and evolution of the lunar crust. And hopefully I've convinced you that current and future thermal infrared observations of the moon and other airless bodies are really important, and they provide important constraints on the formation and evolution of these solar system bodies. And with that, I will end and take any questions.
Okay, thank you, Cari. If anyone has a question for the speaker, go ahead and use the raise your hand function in the chat. Yeah, go ahead, Melissa.
I was wondering about how the Christensen frequency shifts when you're looking at the minerals in vacuum, are you accommodating the fact that a similar composition might shift when you're looking at finer grain materials, and have you optimized for that as well?
Yeah, so I didn't really go into the laboratory measurements today, but that's certainly something that those of us on the diviner team have really spent a lot of extensive time thinking about and doing laboratory measurements. And so the spectra here that I'm showing are fine particulate, and we can tell that these are fine particulate based on these transparency features that we see at wavelengths shorter than the CF, and those at longer wavelengths marked by the TF. And so we do predominantly measure things at fine particulate to be representative of the regolith covered lunar surface. And most of these laboratory measurements that we've been doing have been done under a vacuum simulated lunar environment. And so it does account for the thermal gradients that we experience, or what the lunar surface experiences, and those do affect the laboratory measurements. And so we've really been honing in on lab measurements and comparing them to diviner data to really best simulate the lunar surface in these environment chambers.
Okay, well, thank you, Cari, and thank you to all of our speakers. We are now at a break time. In about 20 minutes, we will reconvene in the plenary room. Thank you.